Dear students, welcome to the 12th online class of Control System Engineering. In previous class we studied second order system and its type: overdamped, underdamped, undamped and critically damped, and their classification on the basis of location of poles. Then we studied general second order system and the parameters associated with it, which were natural frequency and damping ratio. Then we studied transfer function in terms of damping ratio and natural frequency of the system. Now we will start lecture 12. Dear students, by the end of this lecture, you will be able to find settling time, peak time, percent overshoot, and rise time of an underdamped second order system. Dear students, in this lecture we will study underdamped second order systems and transient specifications, which include rise time, peak time, percent overshoot, and settling time. Dear students, let we have a system G of S whose input is R of S and output C of S. A step input is applied and system is underdamped. For underdamped systems we have zeta greater than 0 and less than 1, and complex poles are present in pole 0 map, and time response is shown in the figure. Dear students, now we will find step response for the given second order system. Output of the system will be equal to input R of S multiplied by transfer function G of S. For time response we will use partial fraction, and we will have two terms. First will be forced response, second will be natural response. After finding the values of K1, K2 and K3, we will take inverse Laplace to find time domain relation. Time domain relation for C of t are given here in both forms. Students, in this graph we have step response of underdamped second order system for various values of zeta. As if you see, if zeta equals 0.1, we have high oscillations. If zeta equals 0.2, oscillations are reducing, and if you further increase zeta equals 0.8, you will observe that oscillations are nearly damped out. Dear students, now we will study parameters associated with second order system. Earlier we have studied zeta and omega n. Now we will study parameters associated with response of underdamped second order system. These parameters are rise time, peak time, percent overshoot, and settling time. Dear students, now we will start with peak time. Peak time is the time required for the response to reach the first peak of the overshoot. Students, if you look at the graph, peak time indicates the time at which response have maximum value. Mathematical form is given here. Dear students, now we will develop mathematical relation for peak time. Peak time is the time required for the response to reach the first peak of the overshoot, and this also corresponds to the maximum value of the response. So this can be found by taking derivative of the output response and making it equal to 0. Now we have relation of output c of t. Its derivative will be c dot of t, and its Laplace transform will be equal to as c of s. Now for time domain response, we will take inverse Laplace, and for this we will convert Laplace domain relation of c dot of t into a specific form by completing the square in denominator, and hence using Laplace transform table we will get our desired time domain response. If you see the relation of c dot of t, this consists of product of three terms. First is omega n divided by square root of 1 minus zeta square multiplied by exponential power minus zeta omega nt multiplied by sine function with angle of omega n multiplied by 1 minus zeta square t. Now to find maxima or minima, we will take derivative equals 0. If you look at the equation, among these three terms, omega n divided by square root of 1 minus zeta square consists of constants, so it can't be 0. Exponential power minus zeta omega nt will be 0 at time equals infinity. So for local maxima or minima, we will use sine function value equals 0, and this will be 0 when its angle, which is omega n multiplied by square root of 1 minus zeta square t equals n pi, or time equals n pi divided by omega n multiplied by square root of 1 minus zeta square. Dear students, if you look at the equation from last slide, in this each value of n give us the time for local maxima or minima. Let n equals to 0 give us time t equals to 0, which is first point on the curve shown in the figure and has 0 slope. For first peak, which is peak time, is found by letting n equals 1, and its relation will be peak time will equals pi divided by natural frequency omega n multiplied by square root of 1 minus zeta square. Dear students, now we will study percent overshoot. Percent overshoot is the amount of waveform or response that exceeds from the steady state value or final value of the response at peak time is overshoot, and this exceed amount of waveform expressed in the form of percentage is known as percent overshoot. You can see in the figure, at peak time response have maximum value C max, which is actually exceeded from C final or the steady state value of the response. Students, now to find percent overshoot, we'll use the relation given in the first equation of the slide. In this, C max corresponds to maximum value of response and C final corresponds to steady state or final value of the response. Now we know that maximum value of response, which is C max, occurs at peak time. Now using time domain relation of C of t and substituting time with peak time, we get relation for C max. And we know that for step input, final value of response equal 1. Substituting these values in percent overshoot relation, we get our desired equation. Dear students, in the last slide we obtained relation for percent overshoot. For any given value of zeta, we can find percent overshoot of the response. For instance, if we have percent overshoot of the system, we can also find the zeta using the relation given here. Dear students, now we will study settling time. Settling time is the time required for the transient's damped oscillations to reach and stay within 2% of the steady state or final value. Mathematically, settling time equals 4 divided by zeta omega n, and 1 over zeta omega n equals time constant of underdamped second order system. So settling time also equals 4 time constants. If you see in the figure, settling time is the time in which response of the system reaches and stay within the 2% of the final value limit. In some cases, 5% of the final value limit is also used. Dear students, now we will develop mathematical relation for settling time. Now we know that settling time is the time in which response of the system reaches and stays within the 2% of the final value limit. For this formulation, we will use output equation C of t, which is the first equation of the slide. In this equation, we know that 1 is a constant value and will not change over the time, and it is our final value of the response. Second term consists of product of 3 terms, which includes 1 over square root of 1 minus zeta square multiplied by exponential power minus zeta omega nt product with cos with angle of omega n square root of 1 minus zeta square t minus pi. Now we know that maximum and minimum value of cos function are plus 1 and minus 1. And for the response of the system to stay within the 2% of the final value, then 1 over square root of 1 minus zeta square multiplied by exponential power minus zeta omega nt must be equal to 0.02, and cos function also value plus 1 here, and this defines a band of 2% around the final value of the response. Now solving this equation, we get a relation for our desired settling time. Dear students, now we will generalize the relation for settling time. If you change zeta from 0 to 0.9 in the relation of settling time, its numerator varies from 3.91 to 4.74. So an approximation has been concluded for settling time for all values of zeta, that settling time must be equals 4 divided by zeta omega n. Dear students, now we will find relation for settling time using alternate method. We have equation for time response of second order system whose time constant equals 1 over zeta omega n. The time constant defines the speed or a rate at which response of the system respond to the changes. Students, now if you look at the figure, it represents step response of underdamped second order system whose time axis is divided on time constant. If you look at the response, this response is within the envelope defined by relation 1 divided by square root of 1 minus zeta square product with exponential power minus zeta omega n t, and the response always remains within these envelopes. Dear students, now if you look at the figure, after the time of 4 time constants, the response of the system stays within the limit of 2% of the final value. So settling time is equal 4 tau or 4 over sigma or 4 over zeta omega n if we are using 2% criteria, which means response of the system remains within the limit of 2% of the final value. And settling time equals 3 time constants or 3 over sigma or 3 over zeta omega n if we are using 5% criteria, which means response of the system stays within the a band of 5% of the final value. Dear students, now we will study rise time. Rise time is the time required for the response of the system to rise from 10% to 90% or 0 to 100% of the final value. For underdamped system, rise time is the time required by the response to rise from 0 to 100% of the final value, where for overdamped system it is 10% to 90%. Students, if you look at the graph, as input is applied at time t equals 0, so system response also increases and reaches to final value which is equal to 1. For the first time when it touches the final value of 1, this time duration is known as rise time, and it is also represented in the graph. Dear students, now we will develop a mathematical relation for rise time. We have output equation for a time response of second order system. In this, we will replace time with rise time. And at rise time, output of response will be equal to 1. Making rearrangements, we get the equation that exponential power minus zeta omega n rise time product with sum of cos of omega d rise time plus zeta divided by square root of 1 minus zeta square product with sine omega d rise time whole equals 0. Now we know that exponential term will be 0 at time equals infinity, and this term can't be 0 at rise time. Now solving the cos and sine angles, we reach to tangent of omega d and t are equals negative square root of 1 minus zeta square divided by zeta. Multiply and divide this by natural frequency, we get omega d, which is damped frequency of oscillation, over sigma, which is exponential damping frequency. So the rise time equals 1 over omega d, tangent inverse of omega d over minus sigma. Now if you look at the figure, tangent inverse of omega d over minus sigma equals angle pi minus beta. So rise time of second order underdamped system equals pi minus beta divided by damped frequency of oscillation, which is omega d. Dear students, now we will design components of system using transient response. We will design our system such that must meet the given specification of 20% overshoot and settling time of 2 seconds. In this example, we have a rotational mechanical system having degree of freedom equals 1. Now if we solve for transfer function, we get g of s equal 1 divided by js square plus ds plus k. Now for comparing with general second order system transfer function, we will take j common from the denominator of the transfer function to make coefficient of s square equal 1. Now comparing with transfer function, omega n equal square root of k over j and 2 zeta omega n equals d over j. Our design problem requires that system must have 20% of overshoot and settling time of 2 seconds for input step torque. Settling time is equal to 2 seconds and its relation is 4 over zeta omega n. So zeta omega n equals 2 here. Dear students, from last slide we know that required settling time is 2 seconds. On solving we have zeta omega n equals 2. From equation 4.51 we know that 2 zeta omega n equals d over j. So or 2 zeta omega n will be equal to 4. And this will be also equal to d over j. And from equation 4.52 we obtain 4 over 2 omega n, which is equal to 2 multiplied by square root of j over k. Now we know that required overshoot is 20%, so we can find the value of zeta, which is equal to 0.456. Substituting these values, we obtain 2 multiplied by square root of j over k equals 0.456 or j over k equal 0.052. And from the diagram, we know that k equals 5, so j is equal to 0.26. And we can also solve this for the value of d, which is equal to 1.04 through equation 4.53. And with this we have designed components of rotational mechanical system for overshoot of 20% and settling time of 2 seconds. Now if any of you have any questions, please ask.